Today's lesson is going to focus on probability. For your objective today, students will be able to determine simple probabilities and probability distributions. So in our activator, we took a look at some probability scenarios where we were trying to determine the total possible outcomes of a given situation. In our instructional focus, we're going to expand this idea of total possible outcomes to talk about what a sample space is and to discuss probability functions. So let's take a quick look at that activator. When we thought about a single coin being tossed, we knew it could either be heads or tails. All right, so it had two outcomes. A six-sided die would have a 1, 2, 3, 4, 5, 6, which is 6 possible outcomes. Now, what about three different coins are tossed? What are the possible outcomes? How might you think about it? We could have all three being heads, 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 heads. We could have heads, tails, heads. We could have heads, heads, tails. We could have heads, tails, tails, right? And if we think about each of these outcomes being different, for example, heads, tails, heads, and heads, heads, tails, each have two heads and one tail, right? Are those considered different outcomes? If they are, well, then you're going to have a higher total outcomes, right? Does the order matter? All right, and if the order does matter, that's fine. It just means we're going to get a different number of results. These are the four different possible outcomes you could get with heads being first. You could get the same four outcomes with the tails being first. So you could have like tails, heads, heads, tails, tails, heads, tails, head, tails, or tails, 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 right? Which gives us a total of 8 possible outcomes. So for that one, you could think about it as being 8 outcomes. You could also think of it as you could get 0 heads, 1 head, 2 heads, or all 3 heads. 4 possible outcomes. It depends on how you think about it. I like to look at it in these terms here, in these terms here, where we have, tails, heads, heads, where the order does matter, because these are all the different possible ways you can come up with each outcome. Tails, heads, tails, and tails, tails, tails. Where there are 8 distinct possibilities. All right, that's the one that I would go with. And a way in which we can get that outcome there, 2, 6. This one, each coin had 2 different possible outcomes. So, and we do 3 different coins, so just 2 times 2 times 2 gives me 8 possible outcomes. The same actually works with a 6-sided die. It would just be 6 times 6 times 6, which gives me 36 times 6, which is 216 possible outcomes. If you draw 5 different cards from a standard deck of cards, there's going to be a huge number of outcomes, right? This would be 5 choose 52. If we remember that, with our calculator, that NCR, 5 choose 52. 2 chips drawn simultaneously from a jar containing 10 chips. This would be 2 choose 10. And we could put those in our calculator and get those values as well. I'm not going to go through the process of doing that right now. Just know that's a way you could come up with that. But these are the ways we can start thinking about total possible outcomes of different events occurring. So let's think about some other possibilities. All right. So what I want you to do is I want you to think about the probability of the following events. What would be the probability of tossing a head on one toss of a fair coin? What about tossing 2 heads in a row? What would be the probability of drawing a queen from a standard deck of 52 cards? Or rolling a sum of 4 on a single roll of 2 fair 6-sided dice? What about guessing all 6 numbers in a state lottery that requires you to pick 6 numbers between 1 and 46, inclusive? Go ahead and try and determine these probabilities. And when you're ready, unpause your video, and we'll go over the answers to these probability questions. All right, welcome back. So let's go ahead and take a look at the probabilities that you could have calculated. So for the first one, there are 2 outcomes, tails or heads. So the probability would be 1 out of 2. One of those 2 outcomes is the outcome you were looking for, tossing a head. So there was 1 outcome that you wanted divided by the total outcomes, which were 2, so where the probability would be 1 out of 2. All right. For the second one, tossing two heads in a row. Well, if you toss a coin two times in a row, you could go tails, 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 heads, heads, tails, or heads, heads. Now, the outcome you were looking for was tossing two heads in a row. The total possible outcomes, there were four. So the probability is 1 out of 4. All right. With the deck of cards, there are 52 possible cards you could pull, 4 of which are queens. Well, since there are 4 queens in the deck, your probability is the number of queens in the deck, which is 4, divided by the total possible outcomes, which was 52, because there are 52 cards in a deck, which gives your probability of 4 out of 52, which reduces to 1 in 13. The next one, rolling a sum of 4 from 2 fair dice. Well, you have to think about what are the different possible outcomes. How can we get 4 with 2 dice? You can have a 1 and a 3 and a 1, or you could have double 2s, 2, 2. All right, so there are 3 possible outcomes. Based on our multiplication principle of counting, the total number of outcomes is 36, just 6 times 6, so your probability is 3 out of 36, or 1 out of 12. The last one, the lottery, the number of ways you can pick 6 numbers from 46 is 9,366,819. And if you're going to just take one shot at it, that means the probability of you actually picking the right numbers is 1 out of 9,366,819, which ends up being a very, very low percentage. So in each of those cases that we looked at, we started out by counting the number of possible outcomes in the experiment. All right, the set of all possible outcomes is what we call the sample space of our experiment. So if we ever talk about a sample space, that's basically referring to the set of possible outcomes. All right, an event is a subset of that sample space. All right, so each of our sample spaces in our problems that we looked at consisted of a finite number of equally likely outcomes, and that equally likely outcome is very important when we start talking about probability. When choosing cards out of a deck of cards, we talked about how they were all equally likely, and that way we were able to assign a simple probability of just saying the number of outcomes we were looking for, which were, the outcome of queens, right? The event, divided by the number of outcomes in our sample space. There were 4 queens out of a sample space of 52. We could just divide that, and that gave us the probability of the event. All right, the probability of an event, and this is based on, like we said, equally likely outcomes, because if for some reason there's a greater chance of picking certain cards over others, it wouldn't work, right? It's just the number of outcomes in E, where E represents the event, and we divide that by the number of outcomes in S, where S is our sample. Now, a way in which we can look at the equally likely outcomes, which is really important, is if we go back to that example from before. All right, example D, rolling a sum of 4 on a single roll of fair dice. Well, a lot of people would jump into this and say, well, they could get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And they'd say, oh, that's my sample space right there. There are 11 different possibilities, so getting a 4 is just 1 out of 11. Well, that doesn't work because there are only 3 ways to get a 4 when there are, for example, 6 ways to get a 7. So the chance of getting a 4 should be much smaller than the chance of getting a 7, and so on. And that's what we look at right here. 4 is only one of the possible outcomes, right? But the reason that it's not 1 in 11 for the probability is the probability of rolling a sum of 4 is not the same as rolling a 2 or a 3 or a 5, right? All of these different outcomes do not have the same likelihood of occurring. So we have to have equally likely outcomes in order for this formula for a probability of an event to work out for us. Now, if we wanted to look at this as the outcomes are just 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in that same problem of the sum of 2 fair dice, right? We can assign probabilities to those outcomes in the smaller sample space. So it's consistent with the total number of ways in which that event can occur. So this table here is a probability distribution, all right, where each probability, unique probability, so for 2 it's a 1 in 36, is assigned by a probability function, right? So there's one possible way out of the 36 total in which we can get a 2. There are 2 possible ways to get a 36, or to get a 3, 3 possible ways to get a 4, and so on down the line. All right, we can see that the outcomes here are not equally likely, but we can find the probabilities of events by adding up the probabilities of the outcomes in the event. All right, and we're going to see an example where we can do this. So if we want to find the probability of an event occurring and the outcomes don't have equal likelihood, we can create this probability distribution that we can use to solve the problem. So let's take a look at the problem that we're going to look at. We want to find the probability of rolling a sum that is divisible by 3 on a single roll of 2 fair dice. Well, that means we need to know what are the chances of getting a 3, a 6, a 9, or a 12, because all of those numbers are divisible by 3. So we can come back to this table and I can say, well, I want to take a look. All right, I want to take a look at the probability of rolling a 3, the probability of rolling a 6, 9, and a 12. All right, we had 2, 5, 4, and 1, which gives us a 12 out of 36. All I did was I added those probabilities together, which tells me I have a 1 out of 3 chance, all right, of rolling a sum that is divisible by 3. And that's just what we see here, is that we take the individual probabilities from that probability table and we sum them, and we can use that sum to determine the probability of the event. Now, this is different than when we had equally likely outcomes, right? Because the possible outcomes, right, the likelihood of getting a 3, 6, 9, and 12 were not equal. But we were able to use the probability table to help us to determine a final probability. So now we need to define a new term here, which we call a probability function. All right, a probability function is a function, we'll call it P, that assigns a real number to each outcome in a sample space S, subject to the following conditions. First of all, the probability of an outcome has to be between 0 and 1 for every possible outcome O. The second thing is that the sum of the probabilities of all outcomes in the sample space S, all right, has to equal 1. All outcomes, all possible outcomes, when we add their probabilities together, it's going to give us a 1, because there's a 100% likelihood that something in our sample space will occur. All right. The last thing is the probability of the empty set, or the probability of no outcome, is 0. There has to be an outcome, and that outcome has to exist in our sample space. All right. So if we say the probability of an event where outcomes are not equally likely, we can say let S be a finite, non-empty sample space in which every outcome has a probability assigned to it by a probability function P. So there's some function that assigns these probabilities. If E is in any event in S, then the probability of event E is the sum of the probabilities of all of the outcomes contained in E. All right, and so when we talked about the previous problem, all right, finding a sum divisible by 3, we said E, all right, our event is having a sum divisible by 3, all right? There were 4 different things in that event, 3, 6, 9, and 12. And we said the probability, the total probability, is just the sum of those probabilities. So the probability of the event is the sum of the probabilities of all of the outcomes contained in E. And that's exactly what we did on that previous problem. So how do I know if a probability function actually does what it's supposed to, that it's a legitimate probability function? Well, we can test it. All right, so I could ask the question, is it possible to weight a standard 6-sided die in such a way that the probability of rolling each number n is exactly 1 divided by n squared plus 1? And you might think, well, maybe, I don't know. Maybe we could assign those probabilities for each number. And if we do, we would get something like this. All right, so if I did 1 over 1 squared plus 1, that would give me 1/2. So you'd have a 1/2 probability of getting a 1. All right, and let's just assume that there's science to it, that we can make a die where half the time it comes up as a 1. Well, we plug in a 2, we'd get 1 out of 5 chance of getting a 2, a 1 in 10 chance of getting a 3. These numbers are all determined from this probability function. We're just plugging in the 1, 2, 3, 4, 5, and 6. And when we do that, we end up with all of these distinct probabilities in a table. And we ask ourselves, well, would it be possible to do this? Would it be possible to have a die that does this when we roll it, that we have a half a chance of getting a 1 in 5 chance of getting a 2, etc., etc.? And what we find is that when we add all of these different possibilities together, we do not get 1, meaning it's not valid. This is not a valid probability table because in order for it to work, there has to be a total of 1. If the total isn't 1, this is not a valid probability function. It doesn't work. If the sum of all the different probabilities has to equal 1. Remember the other things, right? Every probability has to be between 0 and 1. You can't have a negative probability, and you can't have a probability greater than 1. All right? And there can't be a probability of getting something that's not in our sample space. All right? Something that's not in our sample space would not be valid, or would have a probability of 0. All right? So let's take a look at a problem where we can actually use a probability function. All right, so we have this scenario. Sal opens a box of a dozen chocolate creams, and he generously offers 2 of them to Val. Well, Val likes vanilla creams the best, but all the chocolates look alike on the outside. You can't really tell which ones. So what is the probability then that both of Val's picks turn out to be vanilla cream? Well, let's start out by taking a look at all of the possible outcomes. All right. The first thing that we're looking at is we're choosing 2 chocolates from a box of 12. So we're doing 12 choose 2. That tells me how many possible ways I could pick 2 chocolates from this entire set. All right. And 12 choose 2 gives me 66 possible outcomes. And we're going to assume they're all equally likely, that there's no preference. We're just going to randomly pick 2 out of the box. All right. So now we want to say, well, how many different ways could we pick 2 vanilla creams? Well, we know that there are 4 of them, and we want to know how many ways could we choose 2 of them to be vanilla cream. 4 choose 2 means 6. So there are 6 out of those 66 outcomes have exactly 2 vanilla creams. So our total probability is going to be 6 out of 66, which is 1 in 11. So the probability of choosing 2 vanilla creams would be 1 in 11. All right, so in this lesson, we investigated sample spaces and probability functions. We applied our learnings to analyze various probability scenarios. You should be able to identify sample spaces and probability functions, and you should be able to determine simple probabilities.